So this is our first introduction to Stokes' theorem, which I keep referring to as a 3D counterpart to Green's theorem. Now remember, with Green's theorem we have to have a vector field, so with Stokes' theorem we also have to have a vector field. But now we're going to have arrows in the room and not arrows just on a plane. So there's going to be stuff next to I, which we call F1, stuff next to J, which we call F2, stuff next to K, which we call F3. Now, instead of having a curve and a region in a plane, we're going to have a curve and a region in 3 space. Now, what this can look like, usually, is think of a flying pancake in space, or someone's throwing up a pizza, and then we take a snapshot, and that's actually what we're seeing. The surface itself we're going to call S. It has 2 sides. If it only has 1 side, we can't do this. And we have to designate which side is up. And that's what we're going to mean when we say S is oriented. All that means is we're saying which side is up. Now, there's a curve that goes around it, and the orientation on the curve is very important. And so what happens here is we're going to call the curve C, and what we want is that the orientation of C is inherited from the orientation of S. From that of S. Now what does that mean? It means if you stand on the curve so that your head is pointed in the direction of up, that the inside of the curve is always to your left as you walk around it. The right-hand rule is actually in play here. We won't have to get that specific, but all we want is, as we walk on C, how about along C, with our head in the same direction as up of S. That the inside of S is always to our left, that the region S is always to our left. In practice, this is easy to figure out. Theoretically, we actually would have to do the right-hand rule between us standing and the vector actually pointing in and the velocity vector as we're walking. Right? And so those 3 vectors that actually have to be in the right-hand rule, but we're not going to have to think about that hard. Now, what kind of conclusion could Stokes' theorem possibly have? Well, the same kind of conclusion as Green's theorem. So the conclusion should look something like, and we'll get more specific, I just want to set the prerequisites here, that the work done around C by the vector field, so we still have arrows pushing stuff around C, we're still going to call it counterclockwise as viewed from above, that should be some sort of double integral where we're putting little patches on S, and then we're going to have a big mess in here, and it's going to have lots of little curl pieces like the kind that actually show up in Green's theorem. So let's put little curl pieces here for the moment, and we'll worry about what those pieces look like in the very next video.